1.1 Functions, Domain, and Range. What we're looking at here is now looking at graphs and seeing how the definition of function, domain, and range apply to graphs. So let's recap a couple of things. First of all, in this question, we're to identify the special relation. If you remember correctly from yesterday, we talked about the definitions. The definition of a function is that it is a special type of relation where for every x, there is only one y. Okay? So that function we have to look for. The second part, what we're going to do is pay attention to the scale on the actual diagrams and to determine the domain and the range of each of these three functions that you see here. Okay, now for the domain, we read from left to right, and for the range, we read from low to high. So, knowing this, we're going to now determine whether each of these pieces are functions. So, if you look across here, every x has only one y. So this first graph will be labeled a function. The second graph, for every x, there is only one y. So I'm going across here. And every x, there is one y. So that is known as a function. In here, I can draw one line, one single line, and it will show you that it is not a function. So you draw a vertical line, known as a vertical line test, and what you do is you cross where the graph touches that vertical line. So you notice that it touches it twice. Now you could have drawn this line anywhere. I could have taken this whole thing, folks, and drawn it anywhere. Okay? I could have drawn it anywhere. And because I can draw it anywhere, as long as it touches the graph anywhere at any point where it touches the graph twice, it fails something called the vertical line test, and because it fails the vertical line test, it is no longer a function. So this, folks, is not a function. Okay, it is just a plain relation. And remember that a relation is anything that is graphable. All right, next, we look at the first one, and we're going to state the domain. If you think about it, we read it from left to right. How far is this going? Look at the arrow. It's going to go on forever and ever. In fact, it goes off the page forever and ever from negative infinity all the way up to positive infinity. So the idea, the domain, goes from left to right forever and ever. So how do we write the set? So domain is set notation, so that curly bracket. X is the domain. Remember, X values imply the domain. Goes on forever and ever. Remember, in both directions, forever and ever. So we say that it belongs to real numbers. It is a real number. It is every number along the number line with no exceptions. That is how you state the domain for this particular line. Goes from negative infinity to positive infinity. Now we're going to look at the range. How do we state the range? Well, it goes as low as forever and as high as forever. So it goes on forever and ever in both directions. That means it goes from negative infinity all the way up to positive infinity. So when we state the range, folks, it's the y values we're looking at, and that means it goes from y goes on forever and ever, so y belongs to real numbers. It's all real possible values. And that is the range and domain for this function. All right, we're going to now look at the second one. We're going to erase what's in front of here and now look at graph B. Okay? And let's look at graph B. Here we go. Graph B. Looking at this, we know that this is a function, So we're going to state the domain. The domain goes forever over here, all the way up to here. So forever in both directions, guys. It gets wider and wider. Every parabola gets wider and wider. So we're going from negative infinity all the way up to infinity. So imagine it's coming from negative infinity all the way to positive infinity. So the domain is x belongs to real. The range is going to be, let's see, it starts here and goes on forever. So it actually starts here. So it starts at -2 and goes on forever. And because it starts at -2 and goes on forever, it has a hard start. So therefore, in this case, we actually have a value that it starts at, and it goes on forever. So y belongs to real, such that y is greater than or equal to -2. So it starts at -2 and goes on to infinity. So all the y values are greater than or equal to -2. All right, graph C. Let's do it on this page. We're looking at this graph. Even though it's a relation, we can still, fortunately for us, we can still state the domain and range. Domain and range is not specific to functions. It's specific to every graph, whether it's a function or a relation. All right, looking at this, here we go. We're reading from left to right. Where is it coming from? It's coming from negative infinity all the way up to 1. So that is the domain. So the domain is going to be x belongs to real. Now, before any of you ask the question, does it always begin with x belongs to real and y belongs to real? The answer is yes. Not 100% of the time, but I would say most of the time you will always have this as your beginning statement. So we're going to have that here. The difference is whether we put a line or whether we put a curly bracket. And that's all depending on the question. For example, in the domain, we can see from left to right, it starts in negative infinity, but it goes up to 1. That means that when we draw this, we have to explain that it goes up to a certain point. So it goes up to from negative infinity, way out here, all the way up to including 1. And it stops at 1. So when we write this out, we're saying x belongs to real, such that, so the conditions are, x is less than or equal to 1. And we close the curly bracket. So again, what we're trying to say here is that it's all real numbers, but that's the such that here, x is less than or equal to 1. Now, for y belongs to real. Let's look. It goes as low as negative infinity all the way up to positive infinity. So this particular graph, it goes on forever and ever in both directions with no restrictions. So we can actually finish the range with just a curly bracket. All right, let's move on, moving forwards. Look at D, E, and F. I want you to take a second to pause the video and determine if each of these graphs are functions or not. Take a moment. Okay, we're back. Now, what we're looking at here is, are these functions? The first one automatically fails the vertical line test because I can draw a vertical line through this vertical line and it touches it at least twice, and I can tell you it touches it infinitely many times. So you would just draw a vertical line, okay, and state that it is not valid. Okay, so vertical line touches it and it's not. Over here, this one is a question that a lot of people have. Is this a function or not? Well, remember that you can draw a vertical line to test. What does it mean when you have a closed circle looking like this and an open circle up here? What does it mean when you have that? And you have another one over here. Well, if I was to draw a vertical line and you were to walk along that vertical line, let's imagine that it's on the ground, okay? And we have a hole on the ground. What does that mean? Oops, sorry. Let's go back. Let's go back and just try this out again. So the idea here, folks, okay, just a moment, please. Okay, so again, you're walking along a line, and then there's an open circle. Well, if you see this on a picture in a painting, you'd assume that open circle means there's a hole there or something going on. That's exactly what this open circle is. It is a hole, guys. And this hole, okay, means that the line gets really, really close to that value, but actually doesn't touch that exact number. So in this case, if we're looking at this hole, this implies that it gets really close to 1, but not exactly 1. For example, like 1.000000001. That is really close to 1, but not exactly. This one is exactly at 1. So again, open means it gets close to there, but doesn't actually touch it, whereas a closed one does. Over here, this open one is at -1. So it means it's getting to a close value like negative 0.999999999, but not really the answer of -1, but really, really close. Okay, and this value is exactly at -1. So when we actually do our test for our vertical line test, I'm telling you right now, this one will pass the vertical line test. So it is a function. So the first one is not a function, and the second one is a function, okay, because again, it passes the vertical line test. So if I was to draw a line, for example, exactly like this, I'm just going to draw a vertical line for you guys. And then I take this vertical line and I draw it anywhere on my graph. What'll happen is as I go move it across, and especially here, it will only touch once. And over here, it will only touch once, and so on. So the graph, for every x, there is only one y. And you know what that means? That means that this particular graph is actually a function. So it's not just a relation, but it's a function as well. And again, if we go across here, this particular graph will also be a function, okay? So the first one fails the vertical line test because you show a vertical line, you show that it touches it twice, and guess what? It's not a function. Second one is a function. So again, the first one fails the VLT. The second one is a function. It passes the VLT. For every x, there's only one y, okay? For every x, there's only one y, so we use the definition. And then the last one, for every x, there's only one y because it also passes the VLT. All right, VLT being vertical line test, if you forgot. All right, D. What are we doing with D? We're going to state the domain and range. What is the domain of this function? Well, if you look at this actual graph, you'll see that the graph, okay, and I'm just going to erase it now, just so that you can see what's behind there. The graph itself is a vertical line. What's the value of x of this vertical line? Well, guys, it's only 2. X is not every possible real value, every decimal, every fraction between a set of values. It is only one number. So it's not x belongs to real, folks, but just x equals 2. The reason why is because it only touches 2 through the whole thing. The range for this is going to be, okay, the range is going to be y belongs to real. Why? Because look at it. From low it goes to -infinity all the way up to +infinity. Now, let's look at graph E. So we're done D. This is the domain and range. Let's look at the graph E. The domain goes from -infinity to here, you might say, but wait a minute, don't forget that the graph continues over here. And then over here it looks like it stops, but wait a minute, it looks like it continues, and it continues on forever and ever. So what are we looking at here? Well, this looks like it's going from -infinity to +infinity, and it does. It looks like there's a break, but remember, horizontally is only what we're looking at. So It goes from negative infinity all the way up to positive infinity, so x belongs to real. The range, though, is a little bit different. Look at the range. It has one value here, one value here, and one value here. It is not all the numbers between 1 and 4, folks. It's only the numbers 1. So the y values are only 1, 3, and 4. So that's what we write. Y equals 1, 3, and 4. And that's because it only touches those values. It's not like it's a diagonal line going through there, folks. So that's why we don't write x belongs to real or y belongs to real. Let's look at the last one, graph f. Looking at graph f, the domain starts from negative infinity. It will go wider and wider and wider, negative infinity, all the way to positive infinity. So the domain of the first one is x belongs to real. The second part, the range, I want you to think of this. This is getting closer and closer to this line, really, really close to this line, but doesn't actually touch it. So it gets closer and closer and closer, but these two shall never meet. We're going to learn about that in this course, about how this particular line gets closer and closer to an imaginary line that we're going to look at later on in this course. So it gets closer and closer, but doesn't actually touch it. Well, the range in this case is going to be y belongs to real, such that what's happening here? Well, the y values are all less than 0. Not including the 0, but less than 0. All right. And there's this, and you can imagine there's this imaginary line that goes across here that the line that the curve does not cross or touch. We're going to be looking at that in this course. That's a graph we're going to have to be, a function we're going to have to graph later on. This one you guys know is a vertical line. This is called a piecewise function. Okay, we do more of these types of graphs in grade 12, but it's a good idea to see these type of graphs now. And this particular is an exponential function. We're going to be looking at functions like this in this course. Okay, and here just an explanation. It's close, but it does not touch. Okay, it does not touch that particular dotted line that you have there. Okay, next, let's look at another function, just this last one right here. What's going on here? Well, we've got some dotted lines, just like we saw earlier, but we have this graph doing some weird stuff. So is this particular graph a function? And the answer is yes, it is a function. The reason it's a function is because for every x, there's only one y. Now, some of you might be thinking, well, what about that dotted line? Well, guys, that dotted line is actually an imaginary line. If you were to graph this on graphing software, this particular dotted line, we don't want to mention the name yet, okay, but we will be talking about this in this course. This particular dotted line is actually an imaginary line that the graph does not touch. So in this case, this is a function because for every x, there's one y. Now the domain of this, we're reading from left to right. So it goes from negative infinity all the way up to close to this line but not touching. Then we jump across this line, and then it goes from here to here, and then we jump across the line again, and we go from here to infinity. So really, the only times that this graph is not touching a line is at these imaginary lines. So x belongs to real, so it's all possible decimals, fractions, whole numbers, all of that stuff, except for, and that's where the such that comes in. So we have the such that here. X belongs to real such that x does not equal, believe it or not, two values. What are they? -3 and +2. Let's look at the range. How far does this graph go? Well, y belongs to real such, and you know it's got to be real because we've got these curves going on. From negative infinity all the way up to, oh, look, it's actually not touching this line. It's close but doesn't touch. So that means what we're doing is this graph gets close and close and close, but does not touch. So that means the y values are actually less than 0. Okay, all the values less than 0. Or the next value that we're looking at, it goes from 1 all the way up to infinity. So y values are greater than or equal to 1. All right, and close brackets. So again, y belongs to real such that y is less than 0 or y is greater than or equal to 1. And that is the value for this part. And again, this is a function, don't forget. Okay, so a lot of times when people understand it, we look at the domain and range of different things. Some people understand it as if you were to draw a number line here, and that's what I kind of had there. Okay, folks, so that's the end of the functions and domain and range of graphs. So I want you to get started on the worksheets that or the homework that has been provided for you. Thanks. Have a numerical day. Take care.